Okay, so in this video, we're going to be looking at tangents and the derivative. So by the end of this lesson, you'll be able to explain why tangents are used to calculate gradients, understand the purpose of differentiation, identify the different notations that we use for derivatives, and find the gradients at different points on the curve using a graph. So let's have a look at the first part, why tangents are used to calculate gradients. Now, when we have a straight line, when we learned about linear relationships, it was easy to find the gradient. Okay, gradient is just rise over run. So here we've got a straight line, and if we were to figure out the gradient of this line, we would use rise over run. So I've just picked from a right angle triangle, and my rise is 4, and my run is 2. So it's 4 over 2, which is 2. Okay, we can see that the gradient here is positive 2 because it's sloping up. And it doesn't matter where on this graph I draw my right angle triangle. The gradient is always the same. If I were to do another one over here, I can see that the gradient is 4 over 2, which is 2. Or if I wanted to do it over here, 2 over 1, which is 2. Okay, anywhere along a straight line, the gradient is the same. One thing that you need to know is when I did my rise over run over here, the reason why we use tangents is because if we would have theta here, the angle, rise is opposite to the angle and run is adjacent. Rise over run is actually equal to tan of theta. Okay, rise, opposite over adjacent, which is run, 4 over 2. So that's the reason why we can use tangents to calculate the gradient. If we knew what the angle was, we can just use the angle to find out the gradient. But what about curves? I've got 3 examples of different curves here. And we can see if we were to find the gradient at any point along the curve, it's going to be different. So if I were to find a gradient at this point here, when x is equal to -1, we can see that the gradient is sloping down, and it's relatively steep. If I were to find the gradient at this point over here, I can draw my tangent, because tangents are used to work out gradients, as I just stated before. It's still sloping down, it's still negative, but it's not as steep. Whereas if I were to find a gradient at this point here, at a turning point, we can see it's got a gradient of 0 because the slope of the tangent is completely horizontal. Up here, when x is positive 1, the slope is positive. Okay, so it's always changing. Here we've got an exponential function. If I were to find the tangent at the curve here, it's sloping up. What about when x is 0? Still sloping up, but steeper. What about, let's say over here? Tangent is still sloping up, but it's even steeper. So we can see that the gradient is not constant, it's always changing. And the last example here, we've got a cubic function. If I were to find a gradient at x equals -2, very steep, and it's positive. Over here, still positive, still steep, but not as steep as before. Over here, oh, it's flat. Gradient is 0. Down here, that's pretty bad. Let's do it again. Okay, it's negative. It's actually sloping down this time. Over here, 0. And over here, positive. Okay, so we can see here that it's or positive, then it hits 0, then it becomes negative, then it hits 0, then it becomes positive again. Okay, so the main point of this is to remember, when we have a straight line, like up here, the gradient is constant. It's always the same no matter where you try, no matter where along the curve you want to find a gradient. You do rise over run. However, for curves, the gradient is not constant. It's always changing. Let's have a look at part 2, the purpose of differentiation. Why do we have it? So calculus begins with two processes called differentiation, which we will study in both year 11 and 12, as well as integration, which we will only study in year 12. So for differentiation, in year 11, we're just going to focus on polynomials and exponentials. And in year 12, we'll go into harder examples such as trigonometry and logs. So differentiation looks at the changing steepness of a curve. Instead of looking at a graph and trying to determine the gradient at a particular point by hand, differentiating a function allows us to determine the gradient function, which we can use to calculate what the gradient is at any point of the graph. So that means once we've worked out a gradient function, when we differentiate, we can just substitute values into x and then we'll know exactly what the gradient is. Here's an example. Okay, we've got f of x, the function is 3x squared minus 2x minus 1. And the derivative, f dash of x, is 6x minus 2. Now, we'll go through how to do this in another lesson, how to actually differentiate. But this here is the gradient function. What does that mean? It means when we substitute values into this equation, we will know what the gradient is at any point for this curve. So this function tells us the gradient at any point along the original curve. So what is the gradient when x is equal to 1? Well, the gradient is equal to 6 times 1 minus 2. Okay, that's from here, which is 4. What is the gradient when x is equal to minus 2? Well, the gradient is equal to 6 times minus 2, minus 2. So 6 times minus 2 is minus 12, minus 2 is minus 14. Okay, it's very steep. So, for example, if we want to have a look at it graphically, here on Desmos I've got it, 3x squared minus 2x minus 1. The very first one was when x is equal to 1. When x is equal to 1 right here, we can see that the gradient is positive, it's sloping up, and it has a gradient of 4. Okay, the tangent at that point has a gradient of 4. But what about when x is equal to negative 2? We can see here that the gradient is negative 14, is sloping down and is very steep. Let's just have a look at here. So when x is negative 2, it's probably around here somewhere. The tangent, if we were to draw a tangent right there, it's sloping down and it's very steep. And the exact gradient is negative 14 at that point. Okay, so the whole point of differentiation is to create this gradient function that will allow us to calculate the gradient at any point along the curve. Alright, so what are the different notations for the derivative? If the function is written as y equals something like 3x plus 2, the first derivative or the gradient function is just y dash or dy dx. Okay, if it's written as f of x is equal to something, then we just write the first derivative or the gradient function is f dash of x. In this course, we'll go up to the second derivative. I call this the concavity function because it tells us whether at that point along the curve it's concave up or concave down. And so when we've got y equals for the function, the second derivative, we just use y double dash or d2y dx squared. if the function is f of x, the second derivative, we just use f double dash of x. Okay. Now this dy dx here, that notation, is pretty much saying we're differentiating y with respect to x. Okay. Let's have a look at how to find gradients using a graph. So here we've got a bottle of water was taken out of a fridge on a hot day when it was 40 degrees Celsius. The graph below shows how the temperature of the water increased over the next 80 minutes. Okay, so here's our graph. What was the average rate of increase in the first 20 minutes? So in the first 20 minutes, we can see, I'll just use green. Here's our 20-minute mark. Okay, here's our 20-minute mark. How much did it increase by? It increased by 20 degrees Celsius across 20 minutes. So the average rate of increase is 1 degree Celsius per minute. However, we can see from this graph that it's not constant because it's a curve, it's not a straight line. Okay, the rate of increase of the temperature is actually changing. Whenever we want to find a gradient at any point along the curve, we call this the instantaneous rate of change. Okay, not the average rate of change, the instantaneous rate of change. So we're going to complete this following table. We just want to find the gradients, because this is the gradient, f dash of x, when x is 0 and when x is 20. So, when x is 0, we can see here that we're using this red line. I'll probably just say it's probably up to there. That looks about right. It's got a gradient of 7, a run of 5. So it's probably increasing at a rate of 1.2, 7 over 5, 1.2 degrees Celsius per minute. Okay, that's a gradient, 1.2. I'll just write that, 1.2. What about when it's at the 20-minute mark? At the 20-minute mark, we've got here, I will probably use, it's probably around here. So if I want to find a rise and run of this, 1, 2, 3, 4, 5, and we've got 5, 6, 7. This time, the gradient is 5 over 7, which is about 0.71. Okay, so what do we notice about the gradients? We notice that the gradients are changing. It's not just changing, it's actually decreasing. From 1.2, it's gone down to 0.71, to 0.35, to 0.17. But because they are all positive, the gradient is positive, it's telling me that it's still sloping up. And we can see that here, that it's increasing, it's sloping up. All the tangents are sloping up along this curve. So it's increasing, but it's not increasing at a constant rate. If it was, it would be a straight line. It's actually increasing at a decreasing rate. That's why it's forming this curve. If it was increasing at an increasing rate, it will actually look like an exponential, or actually look something like that. But this is increasing at a decreasing rate. So I'm going to say the gradients are decreasing, but still positive. Okay, and it looks like it will never be negative, right? Because if the gradient was negative, that means it will end up sloping down. That means this curve will probably come down if it was negative, but it looks like it's approaching 0, or the function itself is approaching 40 degrees Celsius. The water in the bottle will eventually become 40 degrees Celsius, but the gradient itself will be approaching 0. And we can see that here. It's approaching 0. Okay, last bit. Complete the table below of what it could say for the following graph. So here we've got an exponential function. How about I get you to pause the video, have a go with this yourself, and then I'll give an example of an answer. Okay, so I'll just say, for example, when x is -1, 0, 1, and 2. Okay, these are my examples. Let's say this is -1. We can see that it's sloping up, so it has to be positive, but it's not that steep. It doesn't look like it's 45 degrees. So I might say that the gradient is probably maybe 0.5. Okay, it doesn't look like it's got a gradient 1 at 0. Yeah, it looks like it's probably got a gradient 1 at 1. It's probably, maybe it might have a gradient of positive because it's sloping up. Well, steeper than 1, so I'm just going to make up an answer. I'm going to say 1.5. Could be 2, could be 3, it doesn't really matter. When x is 2, it's going to be even steeper than that, still sloping, still positive, still sloping up. So I'll just say maybe that's got a gradient of 3. Okay, so for you, yours will be correct as long as the next gradient is bigger than the one before it. Okay, as long as the next one's bigger than the one before it, and they're all positive. Okay, because nowhere along this graph is it sloping down. Okay, that's it for this video. You can work on exercise 8A, questions 1 and 3.